Okay, in lesson 5.1, we used the finding common basis strategy as well as the one-to-one property to be able to solve exponential functions. So here are 6 problems that I would like you to complete to warm up as a review of what we have covered. And then once you have completed these, I will ask that you unpause the video so that you can check your answers. But just in case you're needing a little push along to get started, let us work on the very first one first. So 9 to the x equals 3 to the x plus 4. So what you want to do is get the common base, the bases to be common. So right now the base is a 9 and a 3, right? And so we want to get those numbers to be identical. So let's do that. So if you want to be using your chart that has been provided for you, that's totally fine. We can rewrite the number 9 as 3 to the second power, and then that x is going to come down, equals 3 to the x plus 4. Okay, so you're looking to rewrite bases so that they are identical, and in so doing, you can then use the one-to-one property to be able to set the exponents equal to one another, and then you have a basic, in this case, linear equation where you can solve for x. Okay, so I'm going to subtract x on both sides, and in this case, x equals 4 is our final answer. Okay, so I want you to do a similar approach for the next 5 problems. Pause at this time and then come on back. Okay, welcome back to this page. So at this time, take a second to check your answers. And as you check, just a couple of pointers that I want to bring to your attention. Again, your goal is to get common bases every single time, and the reason you want to get common bases, as I'm highlighting here in every single one of these problems, is because you want to have the ability of applying the one-to-one property, which allows us to, in essence, remove the bases from the equation, cancel them out, so that you are able to set the exponent values equal to one another to solve for x. Some reminder properties, when you have problems such as number 4 where there is a fraction, right? If you have a 1 over, why is this not writing? Okay, 1, alright, give me a second. Alright, something's happening here. Okay, my pen's just stopped. Alright, there we go. 1 over a to an exponent. A is the base. You can rewrite as a to the negative m. Okay, so keep that property in mind, because in problems like number 4, 5, and 6, you had to rewrite in exponential form the 1/5, the 1/3, and the 1/2. Okay, so I'm going to box this property in. Well, there we go. So just a reminder from 5.1. Okay, so how does 5.1 help us in lesson 5.2? Well, first we're going to do some rewriting logarithms, okay? Now, this is a logarithm. Definition I need you guys to make sure you memorize. If you have an exponential, b to the a power equals to n, you can rewrite it in logarithmic form as log of base b of n equals a. So you will notice down below that I'm going to have you practice writing them in both directions. I'm going to give you a logarithmic equation, and I need you to rewrite it in exponential form and vice versa. So let's start off here. Log base 7 of 49 equals 2. Okay? Log base 7 of 49 equals to 2. So the 7 is the B, all right? The N is the 49, and the 2 is the A, all right? So I'm going to rewrite it as 7 to the second power equals to 49. So notice that the base, or the subscript, sorry, of the logarithm becomes the base, all right? The number is going to be the answer, and the logarithm is always equal to the exponent, and that will be the power, okay? So log base 5 of 125 equals 3. 5 to the third power equals 125. So notice I'm always starting with the subscript. I raise it to the power of this number, and then I take that number and set it equal to that. So in this case, 4 to the negative 1 equals 1/4. Now, if I do from exponential to logarithmic form, obviously I need to write the identifier word log, because I need to say, hey, I'm writing a log function. The subscript of log is going to be the base. The base in my equation is 13. The answer, or the output value, was 169, and I always set the log equals to the exponent value. In this case is a 3. So I'm going to do it again. The log of the base of the output value equals the exponent. One more time. Write the log of the base of your output equals the exponent. So take a moment, pause, and I want you to finish the other 6 problems. Okay, so now welcome back. Check those last 7 problems, those written in orange, and see if you are on track. Okay, let's move on. So, let's do some solving of equations. Now, our equations this time are logarithms, and we're going to solve them using no calculator, okay? Now, I don't mind you using your little cheat sheet if you want to say, look at the common basis to make it quick, but try and not use the calculator, okay, on this section. Okay, so we're looking to solve or evaluate log base 9 of 81. So we're looking for an answer. So what is log base 9 of 81? Question mark is the answer I'm looking for. So I'm going to put an X because that's what I'm looking for, the answer. And when you are given a log equation, what I want you to make it a habit is anytime given a log equation, you need to automatically rewrite it in exponential form, okay? So I need you to rewrite in exponential form. So I'm going to come over here, make a note here, rewrite in exponential form. That kind of did itself. Rewrite in exponential form. Okay, so rewrite that logarithm in exponential form for me. So log base 981 equals x can be rewritten as base 9 to the exponent x equals 81. But 9 to the x power equals 81 is pretty easy to solve for because 9 to the what power gives me 81? Well, I know 9 to the second power gives me 81. So that's pretty straightforward. I don't really need to do common basis to figure something like that out, okay? Because that's simple arithmetic. Let's try this one here. So the 27 to the x power equals to 3. Well, these bases are not the same, 27 and 3, but I know that 27 can be rewritten as 3 to the third power, and then I'm going to bring down that x and equals to 3. So what I need to do is get rid of the common bases, and I'm going to set the exponents equal to one another. Now I know when there is an invisible exponent, that exponent actually is the invisible number 1. So I'm going to divide by 3, and x is equal to 1/3. Okay. Set this equal to x. And I want you now to solve number 17. Let's do this. I'm going to circle which ones I want you to do. I want you to do number 17 right now. I want you to do number 20. What else? Number 25 and 24. So pause the video right now and do those 4 problems, 17, 20, 24, and 25. Okay, let's work these out together. All right. So the 17, I just wrote them in exponential form, but I was going to talk them out with you. 4 and 32 can have a common base of 2. So if you look at your base worksheet, 4 is 2 to the second power. I'm going to bring down that x. And 32 is 2 to the fifth power. So the bases are alike. I have 2x is equal to 5. And if I divide 2 on both sides, I'm going to get x equals 5/2. Okay. 8 and 4, they are on the chart under the base of 2. So 2 to the third power is 8. Bring down the x. 4 is 2 to the second power. I'm going to get rid of those 2's and be left with 3x equals to 2. But I know in order to isolate x, I need to divide by 3 on both sides. So x is going to be 2/3. Four and 2. 4 can be rewritten as 2 squared. Bring down the x. The 2 just comes down, but that's an invisible 1. So 2x is equal to 1. And x is equal to 1/2. Last but not least, 25 and 125. They both end in 5 for sure. They have powers of 5. Bases of 5. 5 squared gives me 25, but I must remember to bring down that x. 125 is 5 to the third. So what am I going to do with 2x equals 3? Well, I'm going to divide by 2 on both sides and end up with x being equal to 3/2. Okay. Hopefully no problems with those. So if you're good to go, in green, circled problems, work out these 4. So again, pause your video, go do these 4 problems, set them equal to x, rewrite them, and solve. Okay, let's do the ones in green. So I went ahead and rewrote them again. Now we need to solve. So notice that once you rewrite them, all you're doing is problems all over again from section 5.1. Okay? 3 and 243 have a common base of 3. So I'm going to put 3 to the x. No changes happen there. 243 is a denominator value, so we're going to write it as 3 to the -5 so that the bases are identical. So x equals -5 is already isolated. No need to solve for x. 4 and 64? Well, 4 can be rewritten and 64 can be rewritten with a base of 4 or a base of 2. I'm going to rewrite it with a base of 4 so I don't have to worry about changing 4 to the x. 64 is the same value as 4 to the third. And when I cancel the bases that are the same, I set the exponents equal to each other and solve and get x equals to 3. You could have done it with a base of 2. You would also arrive to the same answer. Okay? As a matter of fact, we'll do it on this one. Okay? Because these two are 64 and 4, just like the previous problem. Well, 64 is 2 to the what power? It's 2 to the 6 power? Yeah, 6 power. Let's bring down the x. Right? Equals, and 4 is 2 to the second power. Okay? 2 to the second power. Now, okay, sorry. I had a train of thought here. Okay, so I can cancel out the 2's. Now I end up with 6x equals to 2. But what does that again entail? It entails me dividing by 6 on both sides. So x is going to be 2 over 6, which when we reduce is 1/3. Okay. Last but not least, 6 and 216 have a common base of 6. So we're going to leave that as 6 to the x. This is going to be 6 to the negative 3. And I cancel the 6's. We are actually home free already because x ends up being isolated and x ends up being negative 3. Okay, now moving a little bit more upstairs here. So you're going to notice here that sometimes you're going to get logarithms, number 22, where the base here is an invisible subscript. When invisible, next to log, that base is a 10. So where I circled, there actually is supposed to be a 10 there if we felt like writing it in, okay? But lo and behold, it's not. So what you need to do is make a mental note that anytime you see a logarithm with a base that's blank, that base is the number 10, okay? So imagine that being the number 10. So base of 10 to the x power equals 1,000. And how many times do I have to multiply 10 to get 1,000? Well, 3 times. 10 times 10 times 10. X equals 3 will be your answer. Okay? Now over here, upstairs, number 19. If you see an ln, a natural log, so let me come write something up here for a second. Remember that log base 10 of a value is the same thing as log of said value, okay? Just because it's not written doesn't mean it doesn't have a value of 10 for base. It is understood to be 10. Okay, so that's that one. I need you to commit to memory. The other one is natural log of x. Natural log of x is the same thing as log base e of x, where e is the irrational number approximately equal to 2.72. So I need to also have you keep this in mind as you work through these problems. So since an invisible subscript next to ln log implies that that's an e, let's rewrite. E, which is in the visible box, to the x equals e to the 4th. The e's are going to disappear, and you're going to end up with x equals to 4. Okay? Last in this section, let's put this equal to x. I didn't have you guys do number 18, but let's do it together. So rewrite this in exponential form. A to the x equals to 1. And I need you guys to recall that any base value that's raised to the 0 power will always equal to 1. Always. Okay? So 8 to the x equals 1. So 8 to the what power can give me a 1? Just like I finished reinstituting and reminding, is that anything raised to a power of 0 will give you an output value of 1. Okay? And there's some graphing behind that, but we will get to that soon enough. So 21, 23 are your problem. Okay, or problems. All right, let's talk about expanding and condensing. We are almost done. Expanding means to make longer, okay? So make longer. That single logarithm you see right here, okay? I don't want you looking anywhere else but right here in this area, okay? All those problems right there are in need of you using the properties of logs to be able to expand, okay? So we're going to do that. So let us start with log base 6 of 3x. Let me erase this eraser mark. And here we go. So notice that there are two values in this expression that are multiplying. Log base 6 of 3 times x. Anytime you are multiplying, you will rewrite that log as an addition of however many terms you had. And make sure when you rewrite your log that you always make sure to write the base if it's a number other than 10. Okay? Here you have two values that are dividing. So that means I should have two logs. So equals log base 2 of x plus log base 2 of 5. So when multiplying, you expand it to add. All right, now this one's a special one. We have an x and we have a y squared. So the first one out of the 3 we've seen so far that has an exponent. So what do you do with those exponents? Well, right now that exponent is lodged to the y squared, so let's keep it with the y squared a second. Okay, so since those are multiplying, we're going to put them to add. But when you expand the logs, you do not want any exponents, okay? So that exponent 2 has to move because you don't want to lose the exponent. You just want it being used somewhere else. So move that 2 to become a coefficient of the log. So you rewrite it as log base 10 of x plus 2 times log base 10 of y. Okay. Any questions so far? See if you need to pause and analyze that a little longer. Okay, moving on. I'll leave you to the last 3. Last section, condense. You are converting to a single log, okay? Convert to a single log. So what you're going to do is rewrite your sum or your difference of logs into one log. So here, I need to write the word log one time versus the number of times that you've written it. And then I have to look at what those logs were doing. These logs are subtracting, and subtraction translate as division. So 7 over x is what I'm going to write. Okay? The next one, 2 log base 5 of x plus log base 5 of 3. They both have a log of 5, so I'm going to write that down. Okay? I know my final answer has to be a log of 5, base 5. But I need to work with this, and that number. Well, I know that that number has to move back to where it came from, right? So I'm going to move that 2 back as an exponent. So the x now has a squared on it, and it's times a 3. So if you want to write it as log base 5 of 3x to the second power, you know that's totally fine. Okay? Alright. Let's try this one. This is a log base 4. So log base 4, I need to see about the 5, I need to see about the x, and the y. Well, all of them were all adding with one another, and adding implies multiplication. So 5 times x times y is just 5x y. Okay? Last one. Let's do the very last problem on this page. Oh, by the way, this is a typo right here. That should have been a 2. Okay? Alright, so over here, 3 log base a of 2 plus log base a of 6 minus 2 log base a of 4. So, as shared before, we need to make sure that those coefficients go with their corresponding value within the log function. Okay, so we know it's going to be a log base a. 3, join the 2 again, it's going to be 2 to the third power. Log base a of 6, there's nothing, so I'm just going to multiply it by 6. And then I have to divide because of the subtraction, and the 4 has a squared. So if we just simplified, log base a, 2 to the third is 8, 8 times 6 is 48. 4 squared is 16. And when you reduce that, you get log base a of 3. And that's it. Notice how the 3 logs became just 1 log. Alright? Okay, so I think that's about it that we covered in class. I'm going to let you do the other 3 or 2 problems that are left. How many are there? 2 of them. And check with your answer keys. And if you have any questions, don't forget to ask me in class. Or you can send me a remind text. Thanks for watching.